Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we have to do two things, two problems, right, today? Not very difficult. So hopefully, if we finish it a bit early, we can continue on. Okay, so what was the first problem? Sorry? Okay, loot vertex cover, yeah. So we needed to figure out a tree approximation. For, I'll just call it price collecting because that's what it's called in the literature. Vertex cover. Okay? So remember there is a graph. Edges have loot or penalties. Vertices have costs of installing a guard there. And we want to find a set of places to put the guards. And we want to find some subset of edges that will left uncovered. Okay, and we are minimizing the vertices in the cover, the penalty of the edges uncovered. Okay, and the requirement is E minus U is covered by V, by C. Okay, so this subset is touched by these vertices. The guys you don't touch, you pay, right? And this is what you're minimizing. Okay, so who wants to write the LP down? Yeah, do it. Yeah, it's fine. Just write it down. Yeah.
Xi are the
Decision variable, right?
So the penalty edges will be left only when the either side of the nodes are uncovered.
Okay.
This will only happen when x1 and x2 are zeros.
Okay. What if both x1 and x2 are 1?
That's why this case fails in that.
I see. So you have to.
It covers the three cases when either of them are 1 or both of them are 0.
So actually, to fix it, you can just do something like that. If you could do that, right? If you only want to take the positive part. So if it's negative, it goes up to 0 or something. Okay, fine, keep going, yeah. That's it. So this is P12, right? This is Pij. That's it. Okay. Oh, nice. That's pretty compact. Because, you're paying for the nodes and for the edges which are not covered, at least if you could fix this. So how can we fix this?
So actually, these are the two endpoints of the edge which are...
That's right. But you realize the problem is that if both of them are 1, you have a problem, right? So how can you fix that? I'm only allowing you linear constraints. So how can you fix that? One variable corresponding. So add it, come on, yeah. Let's see what this variable looks like. So you're correct. Your formulation is correct, except that it's not linear because of that truncation variable, right? Yeah.
The constraint would be.
Write down what the variable is up here. You have some space. Yeah, XU you already have. Yeah. It's already down there. Yeah. So that you don't need to repeat. It's down here.
Yeah.
Okay. And then?
X UV.
Right. For each edge UV. Good. Good. What is the meaning? Yeah. What if XUV is 1? What does it mean?
That will be, so the constraint would be FU plus
X. Right.
greater than equal to XUV.
Okay. So XUV is going to denote whether you're covering it or not.
Yeah.
So if XUV is 1, you're supposed to cover it. Okay, good. So now what is the objective function? Right, and it's right here. So just modify this. So this will be XVCV, I guess. Yeah.
Same U.
Fine. Yeah. Right.
And instead of this,
Shall
we'll
I
have
I'll just give you something? Okay. So write it. Yeah. Wait. I thought if XUV is 1, you're covering it. Yeah, I think he's right. Yeah. Okay. Yeah, that's correct. Yeah. Good. Okay. Excellent. This is the right formulation. Okay. Everybody here? Great. So can you round it?
so the thing is that
Everybody okay with this formulation, right? There is a variable for every edge which is saying whether it is covered. So that means XUV is the membership in E minus U. Right? And XV is the membership in C, in the cover C. Cool. Okay, let's go on. Yeah?
so what I thought is so we'll get an so here these are integers, right?
No. This we'll relax it. That's right. We'll relax it. Good.
And we'll give it to this
Solver. Okay.
and, it will be X star.
Good. Excellent. It gives you an optimal solution.
So
Right?
what I thought that we can round it like that if X star
Right.
U is greater than 2/3.
If X star UV is greater than or equal to 2/3, good.
Means at least one of them is
1/3 then.
yeah.
Yeah, that's right. Yeah.
So we'll make it 1.
Okay, so write it down, finish it. So if X star UV is greater than or equal to 2/3,
It means at least one of
at least XU or XV,
either
yeah, max of. Yeah,
X star is
okay.
greater than 1/3.
Or X greater than 1/3. Good. So what is your rounding? Yeah.
So X hat
H hat, okay.
star U
Yeah.
will be equal to 1.
If,
X star U
yeah,
greater than
1/3. Okay, good. That's all? Okay. So what is the cost of your final solution then?
so like we are increasing 3 times.
That's only for the XU variables. What about the XUV variables? They are also contributing to the cost.
So we'll then make X U V to be 0.
For these guys.
Yeah. Means if this is
You're there, you're almost there. Just finish it properly. Yeah. Yeah.
this is true, then make X U V
Right?
tilde to be 0.
No. It's 2/3 you want to make it 0? Yeah. Okay, 1. Okay, yeah.
What it would be.
Fine. Okay. So if X star UV is greater than or equal to 2/3 X tilde UV, otherwise it'll be 0, right? Otherwise it'll be 0. But if you make XUV tilde 0, you have to pay for it in the objective. How much are you paying? PUV. How much did you used to pay in the LP solution? 1/3 of PUV. So that also is a factor of 3. Okay? So that's the end of the proof. So is everybody here? Yeah? So if XUV star is at least 2/3, you know by implication that one of the two endpoints has 1/3. So you just round it up to 1. That means if XUV star is less than or equal to less than 1/3, then it will be rounded down to 0. But if XUV is less than 1/3, less than 2/3, then you're already paying at least 1/3 of PUV here. But now, after you round it down to 0, you're going to pay 1 times PUV. So even for the penalty, you're paying factor of 3. So overall, this is a 3 approximation algorithm. Any questions? Why is it 2/3? What do you mean, why is it 2/3? Uh-huh. Why did you pick 2/3, he's asking. Yeah. Right. Yeah. So let me give you another reason why it is 2/3. Maybe it'll help you, maybe it won't. Suppose you say y uv is 1 minus x uv. Okay? So then this is just y uv. Right? So now what is the constraint relating xu and yuv? It says xu plus xv greater than or equal to 1 minus yuv. Right? I just replaced xuv by 1 minus yuv. So now you move this to the other side and you get xu plus xv plus yuv greater than or equal to 1. There are 3 things which sum to 1. So one of them should be at least 1/3. That's his algorithm. Okay. So same thing. Yeah. Thank you. Okay. Great. 10 minutes we are done. Yeah. Okay. So how about, so I have 2 paths now. I can tell you about a primal-dual algorithm for this problem with factor 2. Okay. Or I can tell you about UFL. Maybe I'll do primal-dual now. Might as well, right? You're all like little fresh now. Okay. Then we'll come back to UFL, the second homework problem after T. Okay. All right. So we have the LP with us. Let me take maybe the simple version of the LP, this one. Okay. So let me just rewrite it here. Okay. Right. YUV times PUV is what we are paying.
That is PUV times 1/3.
Yeah.
Why is it?
Okay. So let me finish my description of this algorithm. Let me do it again here. Okay. Thank you, by the way. You guys have it. So this just says XU plus XV plus Y. Actually, let me just call it XUV. At least 1. Okay. Now XUV, right, equals 1 if UV, right, belongs to uncovered edges. Okay. So I'm saying either you cover it from U or you cover it from V or you leave it uncovered. You have to do one of the 3 things. Okay. That's the LP. And all these are non-negative. That's the LP relaxation, right? We'll start with all of them being 0 or 1 and relax it. Okay. So now find an optimal solution X star. You know that for every inequality like this, one of those 3 X star values will be 1/3 at least, because 3 things are summing to 1. Therefore, take everybody who is at least 1/3 and round it up to 1. That's the algorithm. Okay? If you round a node up, you pay 3 times its node cost. If you round an edge up, you pay 3 times its penalty. But that's exactly what you're doing. That's the whole algorithm. Okay? That's just a restatement of your 3 approximation. Okay, so now let's write the dual. Can you write the dual for this? Right? Can you write the dual? Try, you can try it now, come on, yeah. Write the dual for this one. Okay, just like yesterday, you take one, so we have to be careful here. This is for all UV, which is an edge. Okay, so just write one multiplier and start doing your dual thing there. How many dual variables are there? Dual variables. Remember what the dual is? Y's, right. How many Y's are there? Number of equations, which is inequalities, which is number of edges, right? Okay, M, right? So write down the value of the dual variable for this. I guess you can call it YUV. Okay, go ahead. Slowly, take your time, yeah. Mhm. Good. For each vertex, you'll have to see where all the XU comes. Right. Where all will it come? For which all YUV will that XU come? I mean, it's right. Your drawing is right. So there is a vertex U. Okay. You have to see which all edges, neighbors, exactly. So every neighboring edge, right, good. All of those UVIs will have XU in that thing. Good, write it down. Yeah. Sum over V neighbor of U. Yeah, good. Y UV less than or equal to CU. Okay, everybody there? He's just tracing this variable. Okay, this is just another variable like it, so you don't have to bother. What about this? XUVs, where all will it occur? Just one, that's all, just one variable it will occur. Okay, what is the objective function? Summation of, yeah, B is correct, but what is my B in this case? Yeah, think, yeah. P is the right hand side, right? Right.
Each vertex
Right.
So let's say this B, V, U, V1, U, V, K,
Right.
and then we have for each vertex.
For each edge, you mean? Okay, listen, what are we trying to do? Okay, we are just trying to combine these. So these constraints are saying how they should relate to your objective function. But what is your point of combining them? Is to get the highest lower bound. What is the lower bound you're getting by multiplying this constraint by YUV? How much you're getting on the right hand side? 1 times YUV. So what is the total bound you're getting by combining all of them? Summation over all UV of YUV. Yeah, that is the objective function. Right, YUV. And what are you trying to do? Minimize or maximize? This is minimizing.
So this would be maximum.
Right, so write max here. Right. Okay, good. All right. Okay, that's our dual. Thank you. You've done it. Okay, and of course the y's have to be non-negative.
So if we try to derive meaning out of this,
Yes, what is the meaning of this thing? Right, I mean YUV is how much the edge, right, badly wants to be covered. That's basically what YUV is. Okay, and these two constraints are saying, look, you don't want to be covered more than your loot, right? Because if you pay up to your loot, the guy will just forget about you. You know, he's not going to install a guard at one of your endpoints, right? Because if already you pay, you're willing to go up to your loot, that guy will say, just pay your loot and you be on your side. I'm not going to cover you. Okay, so that's this constraint. This constraint says, if there is a very costly guard position U, right? The total amount of how much all the different edges want to pay to install a guard there, this is how much the edge wants to pay to install a guard, cannot be more than the cost of installing a guard. Okay, so YUV is how badly the edge is bidding, it's trying to form a guard at one of its endpoints. It can be trying to bid up, but at some point if it hits PUV, it will say, I'm sorry, you know, like it's not feasible to put a guard here, it's too expensive. Okay, so that's one meaning. Okay, all right, complementary slackness. Who wants to tell me what the complementary slackness conditions are? If I have a pair of primal and dual variables, it's actually quite easy. No, suppose I gave you an X star and Y star, which are optimal duals. Okay. Okay, so I solve the LP, right? And I get one optimal for this, one optimal for that. Okay. if they are complementary dual pair, right? What does the condition say for them to be equal? Excuse me.
For strong duality.
Yeah, strong duality. What does it say? Okay, so remember, this is AX greater than or equal to 1. That's what this is. Right? And this is, well, when I say X, X has a part corresponding to the vertices followed by a part corresponding to the edges. Okay? So now here I'll have Y transpose A less than or equal to C transpose. Right? And remember, Y has variables, as many variables as the number of rows of A, which is just the number of edges. So that's cool. Okay, so Y transpose A less than or equal to C, that's what we wrote down here. Okay, and we also have, our C actually has both C and P in the vector, right? Because X is dotting not just C, X of the vertices is dotting the cost, X of the edges is dotting the penalties. So that's why on the right hand side you have this part. Okay, so what does strong duality say? It says if I've got X star to be optimal, okay, so let's just write down the string of inequalities. Okay, C transpose X star greater than or equal to Y transpose A X star, this is also star, I'm just using that, right, equal to Y star transpose A X star, which is greater than or equal to AX greater than or equal to, let's just call it B. Okay, Y star transpose B, right, which is the dual. Okay, and if both of these are equal, right, they are a pair of optimal duals, right, strong complementary slackness says that this should be tight. What does that mean? That means whenever I have an X star which is positive, right, then this inequality, for this inequality to be tight, the corresponding C should be equal to the corresponding Y transpose A. For that particular, I guess it's a row, right? It's a column, I'm not sure. Yeah, X is a row. Yeah, it's a row. Okay, so this complementary slackness condition will say, now there's actually two types of X's in my problem. Let me write it for XU. So if X star U is greater than 0, right, that means the corresponding C, what is the C for U? It's just C of U. Okay, implies C of U should be equal to the corresponding constraint, this one, right, sum of V, which are neighbors of U, of C Y star UV. Okay, we have another type of X which is X star UV, no? So if that is greater than 0, then the corresponding objective function, which is what? P, should be equal to whatever the left hand side is. It turns out to be just Y. Okay, so this means PUV should be equal to Y star UV. Okay, so both comes from that first one. What comes from the second one? Well, second one, if Y is positive, okay, if Y is positive, then for this to be equal, the corresponding A dot X should be equal to the B. Okay, A dot X is this thing, B is 1. Okay, so if Y is positive, that means the corresponding inequality is tight in the primal, which is just saying X star U plus X star V plus X star UV better be equal to 1. Okay, some of you are looking confused. I have a feeling half of you are not following me. Maybe 1/3. Yeah. But so how did I get this? If I got a pair of primal and dual optima, just for these inequalities all to be equalities, right? These are all just inequalities involving numbers. This is just a scalar number, right? But this number is also this product times this vector. So whenever this vector has a positive value in it, right, the corresponding C coefficient, right, has to be equal to the corresponding y dot A. If not, because it's positive, if this was strictly greater, then this would be a strict inequality. But because these are optimal dual pairs, these values are equal. Therefore, it better be the case that whenever the x is positive, and there are two cases for that, x can be positive for a vertex or for an edge, the corresponding C can either be the cost of the vertex or cost of the edge, penalty, has to be equal to the corresponding dual packing constraint. That's all. Same thing on the other side. Whenever y is positive, the corresponding A dot x better be equal to the B. Therefore, if y was said to be positive by your optimal dual solution, you better have the sum of these to be at least equal to 1. Okay. Now, all this is fine and dandy, but it doesn't get us anywhere close to the 2 approximation we are after. Okay? Because I haven't actually told you very much about it. Okay? So what we are going to try and do to design a primal dual algorithm is we are going to follow what I said yesterday, which is all these other methods which have been defined for good problems, spanning tree, directed spanning tree, matching. Okay? What we're going to try and do is the following. I'll give you the outline here. This is the plan. Okay? In this particular case, we'll start with primal infeasible and dual feasible solutions. Okay? This is very trivial usually. The zero solution does it. Why does the zero solution do it? Because usually you have a covering problem. Covering means you have to install something to cover. You start with zero, it's not covering anything, so it's infeasible.
Sir, but in this case, the answers can be zero as well when the cost to the vertex are very high, let's say 500, and the edges are, the cost of the edges are penalties 1. In that case, our answer will be 0.
No, but then if the penalties are all 1, you will put XUV 1 for those edges, right?
It might be the case that the summation of all these are lesser than the cost to the vertex.
Yeah, but still it's positive, right? How can the solution to this problem be 0? The cost cannot be 0. Look at this constraint. One of these guys has to be a 1. Okay, so when I start with the 0 solution, it's just a covering problem. I'm trying to cover something. If I don't cover anybody, I'm infeasible. That's why it's starting with primal infeasible, 0. The dual is trying to pack something like in a suitcase. But if you don't put anything in there, it's feasible. Right? So that's why the 0 solution for all YUV is feasible. Okay, so that's how we'll start with the 0 solutions. Okay, then we will greedily in some way, so we're back to greedy, okay? We'll some way, maybe greedily, in a clever greedy way, right? I will increase dual variable. Maybe I'll increase 1, maybe I'll increase 2, maybe I'll increase a whole bunch. Okay? And when I start increasing the dual variables, right? Remember what dual variables are? They are just the y values. But they have an upper bound. So somewhere something will prevent me from increasing it too much. Okay? So I'll greedily increase this until some dual constraint is tight. Tight means becomes equal. Okay? Now what happens? Okay, let's look at complementary slackness conditions. If the dual constraint is tight, Okay, let's think of a simple example. We have an edge whose loot value is very low. So we start increasing its y value, it hits the loot. So if the yuv equals puv for that edge, what does the complementary slackness contains say? Oh look, yuv equals puv, which means I can't set the corresponding x star to be positive. Okay, let's just make it 1. Okay, so this is a covering problem. I need to choose some edges, some x values. So if any dual constraint becomes tight, I'll take the corresponding variable in the primal and I'll include it in my solution. This is where I'm using complementary slackness. Notice that I will never be able to find a final solution where these 3 conditions are going to be strictly obeyed. Because if it is, then primal equals dual and I'll actually have given you an exact algorithm. But I can't design an exact algorithm. This is an NP-hard problem. I'm just like trying to follow what are the good properties of a nice primal dual pair. That's all. So if one of these guys become tight, I'll make that guy 1. Okay. So until some constraint becomes tight, make corresponding primal variable equal to 1. Just take it. I mean, you can make it any number, but just make it positive. Okay, now, clearly, the dual variables you were increasing before, they cannot be increased any further because they're already tight. So just repeat. Just go somewhere else. Take some other dual variable, increase it. Okay, now the question is, why is this going to terminate in any way at all? We have a fixed number of variables, but what if all of them are tight? We stop, but why is it a feasible solution? Because whenever we found something tight, we included one of the endpoints in my primal solution. So if everybody is tight, that means for every edge in the graph, I have found something, either the xuv or the xu or xv variable to set to 1. That means I'm already finished covering them. Okay? So that's why continuing to increase the dual value of any variable which can be increased until it becomes tight. When it becomes tight, looking at who made me tight, right? And then picking that guy to be 1 to cover this edge and other edges it covers, right? Is going to give me a feasible solution. Very simple, right? That's all. So that's the whole algorithm. Okay? Now all of these algorithms have one problem, which is you have to figure out who you're going to increase a little carefully. Okay? In our problem, it wouldn't matter. You can increase anybody you want. Take any edge you like and increase it. Okay? That's all. So in this, I designed this exercise for you so that you can do it any way you like and you'll still be okay. Okay? But there are other problems, for example, like Steiner tree, where you can't just randomly pick any constraint that is not tight and start increasing it. You have to increase everybody at the same time. So some other nuance has to be there. Okay, but let's finish this one. Is the plan clear, right? So the plan is clear. Let's just finish it off, okay? So I have dual, I have primal. This is complementary slackness. I don't need complementary slackness anymore. Okay? Can you remember these constraints? Yeah, so maybe I'll just keep the dual constraints. This is quite easy, right? Just remember this, okay? Either the endpoint u or endpoint v or the uncovering variable. Variable saying I'm not going to worry about you, have to sum to 1. Okay. So let's just implement this algorithm. Okay? So we start. I feel like I should do an example, but I've not prepared one. So let's see. Let's do it. So all the edges have some loot value. Okay? All the nodes have some covering value. Okay? Let's say the loot value is very low here. Okay? But it's very high in other places. Okay? And let's say the edges, the nodes are such that the costs are all kind of reasonable. Actually, I should have at least different numbers, so when I call them out. Because the whole point of the algorithm is to figure out what primal solution to pick. So if you start with something, then you don't have any idea, right? See, the whole point of a primal dual algorithm is to figure out what nodes and edges should be in the primal solution. But suppose I just try to be clever and pick some set, right? Then it's not even clear to me that, first of all, that they correspond to any complementary slackness condition, because I've already picked something, right? And maybe what I picked is not such a good idea. Okay, so it's very natural to start with the zero pair of solutions. Okay, all right, so what will we do? Pick any edge you like. Okay? Pick some edge you like. 30, yeah? Okay, which is 130, good, okay. So start with this 130. Okay, I guess I need to call them all something. Let me call something E1, E2, E3, E4, E5, E6. Okay, and vertices U1, U2, U3, U4, U5. Okay, so I pick the 30 edge and I start increasing Y30. Okay, how high can I make it before one of these two guys complain? Okay, Y30 participates in this constraint for 7, this U4, participates in the constraint for U5, which is 4, and it has its own 30. So I can increase it until the minimum of those three numbers, 4, 7, and 30. So I'll start by setting Y6 to be 4. Right? Because I'm increasing Y6. When will it stop? Well, 4 will complain first. Remember, the constraint says this plus that at most 4. This plus that at most 7. This alone is at most 30. So the first thing that will block will be this guy, because it has the lowest value, the lowest constraint. Okay, so I'll stop there. Because this node U5 blocked me, right? I should set its variable to be 1, right? So I'll make x5 to be 1. Okay? Now, pick another variable to increase. Okay, let me suggest one. Can I increase E1? Not no need. Can I increase E1? No? Why not? Yeah, not only is it covered, it's tight. This endpoint has already got a total of 4 sitting on it. So I cannot possibly increase 1. So this is kind of dangerous. I can't increase 1. But as somebody else observed, this endpoint is already covered, because that was the condition I used. When somebody got tight, I put it in my solution. So actually the algorithm has a nice structure. You pick any edge, you keep on increasing it. Okay? Until either an endpoint complains, okay, or its own constraint complains. Okay? So let me try to change this number to illustrate that next. Okay? So its own constraint complains. Whichever one complains, when it becomes tight, you take the maximum that this y value can be. Whoever complains, you make them 1. But let's say the guy who complained is U5. Because you made it 1, you just forget about all these guys right now. Because you're finished with them. You're finished covering them already. By putting a guard there, you don't need to worry about E1 anymore. So in this algorithm, E6 is gone, E1 is gone. Now tell me who you want to raise. Let's say we raise E2. Okay? So when we start raising E2, so at this point you delete E1. Because you don't need it, right? And then E2 you start increasing. Who will complain first? Which one? The 2. Its own constraint will complain. So you take E2 until 2. So then I'll set Y2 to be 2. Right? Now what? Is U3 covered? U1 is covered. Who is U1? U1 is not covered. Because I only filled it to the extent 2. It's not overfilling yet. So what do we do now? When this guy becomes tight because of this constraint, what is the corresponding primal variable? XUV. So XUV, which unfortunately is XU2U1, right? X of edge 2. Right? XUV is X of edge 2. That better be set to 1. Okay? Should I relabel my edges so as to not cause any confusion? Everybody's okay? Or yeah. So edge 2 now has to be set to 1. That means, basically what we have realized is, look, this gallery only has loot 2. The gods at this side cost 5 and 3. It's too much. So I'm just going to pay the penalty for it. Get rid of it. Okay? Alright, so now I can't delete anybody, right? Because I only paid for this guy. Okay? So I can't delete anybody. Let's continue. Okay? E1 is gone, E2 is happy, E6 is happy. Anybody else you want to pick? Pick somebody, come on. Huh? E5, okay, fine. Let's try E5. Okay, so E5, how much can I increase it? Can you actually increase it by 6? Okay, let's see why, okay? When E6 increased already to 4, E6 packed some of this suitcase. This suitcase is 7 units big. But E6 already packed 4 units of it. Right? That's what Y6 did, right? When Y6 increased, it packed this side too. So how much space is left in the suitcase? 3. So Y5 can only be made 3. Okay, so Y5 is now made 3. At that point, which constraint becomes tight? This guy, that vertex. That is vertex U4. U4 becomes tight at that point. Aha. So if U4 becomes tight, what should I do in the primal? I should set X of 4 to be 1. I should put it in my cover. When I put 4 in my cover, who should I now not worry about? E4, E5. Okay, so notice that I have increased this to 3. Okay, there's only one edge left which is not covered. Okay, and it's this guy. How high should it go? 3. Why? Because 2 of it is already eaten up there. Therefore, the remaining 3 is left. So I'll now finally make Y3 to be 3, and that will in turn set U2. Right? Oh, both of them get tighter. Wow. So this also has 3 left, that also has 3 left. So at this point, you can pick whichever one you like to do the covering for this edge. Okay? So this is U2, this is U3. I'll take 2. 2 is smaller than 3. Okay, so I'll take U2. So look at this case. Both U1, U2 and U3 are tight. Just pick one. Let's say X2 will be 1. Okay? So that's our primal dual algorithm. What is our final solution then? What's our cover? I picked 5. I picked edge 2, not to cover. I picked X4 and I picked X2. So the vertices are U1, U2, U5. Okay? And the uncovered edges are edge 2. Right? Okay, let's make sure it's okay. If I get rid of edge 2, right? U1, thank you. U4, U5, yeah. Good. Okay. No, actually this is edge 2. Oh, I see. U2 also is there. Oh, sorry. There is no U1 at all. There's no U1 at all, right? So it's U2, U4, U5. That's the correct answer, right? I first got U5, then I got U4, then I got U2, right? And here I got E2, H2 in my uncovered, okay? Is that feasible? Let's make sure it's feasible. E2, I got rid of it. I want a cover for the remaining, and I got U2, U4, U5. That's fine. Okay. So now, sorry? Good, excellent. So now you can look back and say, I started my algorithm with H2, right? And I gave it a variable of 2. But much later in the algorithm, I chose U2. Right? In the very end of the algorithm, I chose U2. So when I picked U2, I actually put a guard here. Even though in the beginning I thought it was too costly, somebody else paid for the other endpoint. Right? And basically I installed a guard there. So at that point, I can improve my solution a little bit, right? By just saying, if ever I picked an edge to have x of edge value 1, but later in the algorithm, one of the endpoints gets chosen, I'm not going to pay penalty. Like I can basically just get rid of this guy. Because still it's a feasible solution. Okay? This is some kind of cleaning up. Okay? So while I'm going along, I'm just like putting everything in the bag. In the very end, I realize I've actually done more work than I need. So I just go back and clean up all the guys I don't actually need to put in the solution. So this would be like a cleanup step. Okay, so now this is our algorithm, okay? We start, pick any edge you like, increase its dual, something becomes tight. If it's one of the endpoints, you put that guy in, okay? But make sure that, when you increase this guy, you are loading both the endpoint suitcases, right? And keep going. Some other times, what may become tight is its own suitcase, at which point you put the edge in the uncovered set. Keep going until everybody is done, is tight. At which point you have a feasible solution. Then go back and examine if you picked any edges to be uncovered, which were covered accidentally or incidentally later. Okay? If so, then just delete them from the uncovered set. Okay? Now, what we have actually done, if you think about it, is we have come up with an algorithm to set these variables. Right? In particular, just like I filled out the primal solution, let me fill out the dual solution. What is the primal solution? I set all of these guys to 1. What is my dual solution? Okay, y6 is 4, y of edge 2 is 2, y of edge 5 is 3, and y of edge 3 is 3. Right? And they obey the constraints of the dual LP by construction. I mean, that's how I increase them. Made sure I didn't violate anybody. How much money have I collected in the dual? 4 plus 2 plus 3 plus 3. 12 rupees. Right? How much am I paying in the primal? How much is U2? It's 5 rupees. U4? U4 was 7, huh? 7 rupees. Okay, 7, yeah. And U5 is 4 rupees. Okay? So I paid, 16 rupees. I collected 12 rupees as a lower bound. I paid 16 rupees. What is my approximation ratio? 4/3. 16 by 12. Yes? Because I found a dual. By weak duality, every dual is a lower bound on a primal. But along with the dual, I found a primal whose value was 16 over 12 times the dual. Therefore, I have a 4/3 approximation in this case. Okay? Now, all I asked you to prove or think about, or said I will prove, is that this ratio is never more than 2, which is better than a third, right? Because the earlier algorithm is factor of 3. So now I'm claiming this algorithm never pays, in terms of the nodes and the uncovered edges, 2 times more than the money it collects. Okay, why?
Because when you pick up, when the bucket is being filled,
right.
at most fill for the 2 bodies.
That's right. That's it. That's actually the whole proof. In fact, that is the whole proof. Why am I not paying more than twice? Because when I'm filling these Y buckets, right, I am loading actually 3 constraints. One for one endpoint, one for the other endpoint, and one for its own constraint. Okay? Now let's look at our final cleaned up solution. Let's look at our cleaned up. So I'm actually commencing the proof of 2 approximation now. Okay? I'm trying to argue that this greedy algorithm modified in this way is a 2 approximation algorithm for, okay? So claim sum over edges of YE that I collect multiplied by 2, okay, will pay for the cost of the vertices in the cover and the cost of the penalties in the uncovered elements. Right? See, this is the solution I made by this Primal-Dual algorithm is this tilde solution. Okay, I'm now trying to prove this in general, in complete generality. Okay, here's the proof. Okay, take this pair of solutions, XE and YE. So this is just CU times XU tilde, which I made 1 according to this. Okay, all these are tildes. Okay, and this is PE times XE tilde, like I made XE tilde 1 here. But later, remember, I cut it down to 0 when I cleaned up. What does cleaning up tell me? Cleaning up tells me if there is an edge which belongs to U tilde, okay, and I still left it in the final solution. Why did I leave it in the final solution? Why did I not clean this up? Because both the endpoints were not chosen. See, in this case, I accidentally chose this endpoint. That's why I cleaned it up. But if neither endpoint was chosen in my X tilde, in my C tilde solution, right, it will still be there. So this belonging to U tilde implies neither U nor V, right, U or V do not belong to the cover. Right? This is by cleanup. This is what we know. Okay, now let's ask ourselves, how much money are we paying for all the U tilde guys? Okay, well, who made that edge become tight? Only itself. Only itself. Right? None of the neighbors contribute to this constraint. So if an edge became tight and thrown into U tilde, that means Y of E equals P of E in my solution. Yes? Excellent. Second property. Does this Y of E pay for any other node in my C tilde solution? No, because this guy is not in C tilde, this guy is not in C tilde. So this node, this edge, paid only for U tilde, for the PUV. It kept increasing the dual value of these guys, but they never got tight. So that means they are not in C and I'm not paying for them. Great. So the part wherever I picked uncovered edges, they are paid for by the dual solution of that edge itself. Excellent. So that part is done. Now let's do the other part, which is the part corresponding to a vertex V, which belongs to C. Let's call it W. Okay, so I have a vertex which is sitting in C tilde, sorry. Who paid for it? How did it become tight? Well, sometime in the algorithm you picked some edge sitting, touching it, increased its Y value. Okay, but that guy stopped. Why did it stop? Because the other endpoint maybe complained. You know, this guy was 10, that guy was 2. When this guy went to 2, that guy complained. So that edge stopped growing. Okay, then somebody else came, started growing. Maybe again that guy stopped because the other guy complained. So like this we went on until finally the complaining vertex became W itself. Okay? But we know the sum total of all these y values is exactly equal to what? Equal to C of W. Right? That's what it means to be tight. That's how I filled that suitcase. So the money I am paying, okay, so this is for the Y's in U tilde. Okay, now I'm going to do an argument for the W's in C tilde. Okay, for all W in C tilde, okay, C of W, this is the complementary slackness condition, right, is equal to, one sec, sum over U, which are neighbors of W, of Y UW. Yeah.
If value of U2 is 2,
Yeah.
and you are looking at E2,
Right.
then what will you do? You will pick.
There are two choices. You can either pick the vertex or you can pick the edge itself. Okay, both cost the same. So I would say, why don't you go pick the node? It does more work for you. That's what I would do. Right? Because in addition to covering that edge, it covers other people too. So, for the same cost, right? Why not? Yeah. Okay, so back here, this is the complementary slackness condition. Why did I put the node W in my set C tilde? Because it became tight. Okay, so if I sum over all of the W, so now this is true for every W, let me just sum over all the W. Okay, so I think at this point I'm going to get rid of this example. Okay, so sum over all W in C tilde of CW equals sum over all W in C tilde of this. Okay, the sum of the neighbors of W of their Y value. Right, I'm just substituting. Now I'm going to change the order of summation. This is equal to sum over all the edges of YE times the sum over all the nodes in C tilde times whether that node is an endpoint of E. Right? I mean, if that node is an endpoint of E, I have to pay YUW. Right? So now I just pull the Y in the front and I just have to pay, so let me just again call it UW, UV. Okay? And this is going to be either 0 or 1 or 2. Okay? In fact, this amount is going to be exactly, right, the intersection of UV and C tilde. Right? I mean, whenever that node is in C tilde, that edge pays for it. Right? Whenever that node is in C tilde, the edge incident on it pays for it. So now I'm reversing my view and I'm looking at an edge and I'm saying, who all do I pay for? Well, I pay for all my endpoints who are in C tilde. That's exactly this. But how many endpoints, this is your point, how many endpoints can there be for an edge? At most 2. So this is at most 2 times YE. Because this is at most 2. And here is the key point. The edges that are in this sum are not in this sum. The edges that pay for PE are disjoint from the edges that pay for the vertices. So when I put them together, the edges which pay for the U part, they only pay factor 1. Whereas the edges that pay for the node part, they pay factor 2. So in fact, I have something slightly better than a 2 here. Right? I can split this into the edges which are in U tilde and those which are not in U tilde. For the edges which are in U tilde, I only pay 1 times YE. For the edges which are not in U tilde, I pay at most 2 times Y. Okay, so in fact, even though I asked you to prove a 2, I'm getting a slightly better than 2 approximation. So I'll just write it down completely here. Okay, so which implies sum over E in U tilde YE plus 2 times sum over E not in U tilde YE, upper bounds sum over E in U tilde PE, that's this part, plus sum over U in C tilde of CE. Yeah. Contributed 2, that's right. Otherwise, they only contributed 1. Yeah. Even within the right hand side, you're right. So this part also, it's really an inequality, right? Only some of them paid 2, others paid only 1. Yeah. Okay. So what have we shown? Now think about it. Y is a dual solution, okay? And this is actually a primal solution, which is feasible. And going back to my old picture, right? Here is my LP solution, this value. Well, actually, the LP optimum is somewhere here, okay? The integer programming value is the optimum value of this problem, okay? We also don't know where that is. What our algorithm has done is picked up some dual solution here, okay? That's the Y solution, okay? So this is Y tilde. And it has created a primal solution, which is X tilde. And it has argued that this gap is at most 2 times. Okay? So earlier we were saying, if I just take the LP optimum multiplied by 3, which is what we did when we started, I get 3 times ZLP, and that's a feasible solution, therefore it sandwiches ZIP. That was the idea in regular rounding algorithm. In a primal dual algorithm, I don't care about ZLP, I don't care about ZIP. I care about a dual and a primal whose ratio are bounded by 2. Therefore, they automatically sandwich both ZLP and ZIP. So this is even better. I don't have to solve a linear program, right? It's a very clean algorithm. Usually these algorithms run much faster than an algorithm based on LPs. Okay? They are combinatorial in the sense you don't have to take any determinants or anything, right? Because you'll just be like, increasing and decreasing, adding, subtracting, comparing, right? That's what our algorithm did, right? Just kept increasing until somebody got tight, put somebody in, deleted some guys, and took some differences and continued. Okay, so that's why these primal dual algorithms have been very popular for a while, even for problems like for instance, finding a perfect matching of minimum cost in a graph. Okay, you can solve that problem using linear programming. I can write a linear program and if you give it to a linear programming solver, and it will come back and give you a good solution. But still, there is a famous algorithm of Edmonds which doesn't solve a linear program. It tries to find a small matching, okay, and it tries to see if it can improve the cost of the matching by doing these updates. So that's one of these primal dual combinatorial algorithms. And it's really quite elegant because you don't have to worry about solving the LP and all of that and all the numerical issues, right, with it. Okay, so that's my 2 approximation for price collecting vertex cover. So now we'll come back and after about 30 minutes, we'll come back and do rounding for metric UFL, uncapacitated facility location. So we'll start by writing down the LP and then we'll round it. And then I think I might have time to also do primal dual for Steiner tree. Maybe I can do that also. Let's see, okay? We'll stop for about 30 minutes, yeah.